Good afternoon. Welcome to the stream. We're back. We're going to do some more essentials of compilation today. Today, I hope to update the passes that are related to register allocation. So the things that we need to think about on this particular update are we have a whole new set of constraints there. So we have some registers that are reserved specifically for. There's one for the root stack. I think there's one for. I forget exactly which one it is, but there's one for the allocation bits when we were generating the code for that. We saw that there was an explicit register used there. In addition to, we have some that are for various pointers and so forth. So we're going to need to make sure that those do not get allocated to variables. And then there's also some things with making sure that we don't put. I'm gonna have to refresh my memory. I read it earlier today in preparation for this, but it's something with like where we put pointers to vectors and so forth. So we're gonna have to make those phases deal with those correctly, and then we should be able to. Hopefully, if we get through those, we should be able to add the output of those passes to the compiler explorer that we worked on last Monday. So we'll probably have to add some pretty printing, and probably is going to be mostly copy pasta from the other one. With some small modifications, but yeah, it's going to be. I think it's going to be an interesting session. So the other thing that's going to be interesting is Gleam 1.13 came out. So I just updated my local version of Gleam, and we're probably going to have to have a look at that. So let's get started and make sure that we're not breaking anything. So I did already run brew upgrade on all that stuff. You can see my Gleam is updated to 1.13. Node.js is updated to 24.10. And we're going to figure out what we need to do to update our standard library. Yeah, so it updated the standard lib to version 0.65. Lustre got updated, Gleam OTP got updated, and Gleam HTTP got updated. So yeah, so we can also upgrade our Lustre dev tools, but yeah, let's go ahead and do that. I think we're gonna change the constraint here. Oops, need quotes. So we'll support the semver on that. Okay, so we jumped to new version of Lustre Dev Tools, and let's do Gleam build. Make sure that our stuff builds and all our dependencies are building. Okay, we're gonna have to deal with unwrap both. Oh, I'm sorry, that's inside Mist. We use it. No, that's in one of our packages. So it's going to be a little bit before that stuff gets updated, but at least we are currently still building. And let's run our tests, make sure we didn't break anything. Okay, so all of our tests that we had from last session are still passing, and we've successfully updated Gleam. Yay! Okay, so let's have a look at the book. We kind of finished our bits here, and now their example includes register allocation. No, I'm sorry. They've got variables. We verified that ours kind of looks like that. So although I don't know that we got to the end of explicate control, so we did not pretty print our x86 yet. Yeah, so we had this helper module called pretty, and it's just giving us the stuff to be able to output some things to plain text. So I think that let's look at our explicate control pass, because I believe what we were outputting there, let's see, no, it outputs C2. So we did select instructions last time, and it uses this x86 global language. So if we want to be able to print that, we have to go into that language and add the pretty printing. And I don't think that we have any x86 assembly pretty printing yet. So I don't want to spend a ton of time on that. So maybe what we can do is, God, I feel like we did this though. Did we not? Where would we have done it though, is the question. Okay. Yeah, we didn't do any of this. Okay. All right, well, let's have a look at the book, and we'll look at register allocation. Okay, so as discussed previously in this chapter, the garbage collector needs to access all the pointers in the root set. So we have a special stack for the root set. So that is all variables that are tuples. It will be the responsibility of the register allocator to make sure that the root stack is used for spilling tuple type variables. And if a tuple type variable is live during a call to the collector, it must be spilled to ensure that it is visible to the collector. So basically they're saying if when we get a variable that has a vector, so in other words, if we go back to our select instructions, when we did this allocate step, right? And we put the tag in there. We're moving the 3-pointer. And then so whenever we have this move from R11 into a variable, we need to make sure that this variable gets spilled to the root stack. So this is, we're gonna move from R11, which is what we're using to store the free pointer temporarily. So this is why this cannot be cannot be allocated to a variable. And then we need to make sure that this is some dereference into the root stack. That's what they mean by spill. So spilling it onto the stack. The root stack is a special stack. It's not the main call stack. So it's not off of the RSP register or the RBP register, but it is a special space that we have allocated at the start of the program, and and we will like track where that is in R15, because if you see, we used R15 down here somewhere. So R11 is for the, yeah, for vector manipulations, so addressing vectors. And then, so collect is, R15 is the call to collect. So R15 contains the pointer to the root stack. Okay. So when we're calling allocate, right? So actually we need something off of R15 needs to yeah, something off of R15 needs to be the spot for this variable when we're allocating. Okay. So if a tuple type variable is live during a call to the collector, okay, it must be spilled to ensure that it's visible to the collector. Okay. So the latter responsibility can be handled during construction of the interference graph by adding interference edges between the call live tuple type variables and the callee save registers. So they already interfere. Okay, so the callee save registers, we have a list of them. The caller save registers, they already interfere with. Okay. The type information for variables is in the program form, so we recommend adding another parameter to build interference to communicate this A-list. Okay, so we need to probably have a look at what our select instructions outputs, because I think that we were not passing the type information through. Right, so we have this info. And it's just, you know, dictionary of string to list of strings is the type on there. Let's see where that's used. Okay, final references doesn't work yet. Oh, and I should, since I have a new Gleam, I should restart all servers. And hopefully it'll get the new Gleam language server. All right. So expose allocation. Not expose allocation. Explicate control. There we go. Okay, so it's just creating an empty dictionary there. And I think that we might need something more. Yeah, like in this phase, this monadic language with allocations, which are these vector things, it's still only the whole program is one expression. But when you do explicate control, you turn it into a bunch of blocks with go-tos and things. And I think that I'm trying to remember where we used this info. I don't see it referenced anywhere, because this phase, we go down to the diagram here. This is the only phase that produces this, and then it immediately goes into select instructions. So we're not actually capturing the type information here for variables. And I don't think we ever used this info. Like, remember in Racket, it's just an A list, it's not typed. You can have any right-hand side for any key in that association list. So they're saying, hey, we already have the types. No, we didn't. So I think that we're missing something here. The type information for variables is in the program form. So we recommend adding another parameter to the build interference function to communicate this A list. So let's look at build interference and see what it did. Now this, this is using an older version here, so we need to switch this to x86 global. We will discover some things that'll break for sure. And we'll have to refresh our memories about these rules, right? Because this is not a big phase, but I think that it contains a lot. Now, the other thing that we could do, I don't know that it's that reliable, but we could, because the select instructions pass takes this C program and produces an x86 program, and it's going like, hey, this allocate, this only happens for vectors, right? So we have the type here, and there's an assignment to a variable. So maybe what we need to do is take this type here and associate it with the variable there. And then, yeah, let's go to select tail. Okay, so yeah, what we need to do is, I think that in this pass, we need to extract that type information, and we need to put it into here. So the x86 program needs to get some type definitions. Yeah. So we'll add that. Where Where's the definition of our program? Okay, so types is a dictionary between a string and an L dot type. And we don't have L in here, so we're going to say import EOC langs tup as L. And then when we, go on our next iteration and make a new high-level language that has a new feature, we can just update this alias and there will be nothing new there. So select instructions, we've already got that in here. And I think that we need to we're gonna have to change this from a map values to a fold. Not there. Let's look at the Gleam standard library. By the way, if you want to follow along with our updates in code, they'll be here. Sean Cribb's Essentials of Compilation. Okay. So if we do dictionary, there's a fold, but there's no fold values. So so what we want to get out of here is we want the blocks. So I'm going to say, we'll say like let init is going to be a pair of a dictionary and a dictionary, right? So this is going to be the types dictionary, and this is going to be the blocks dictionary. So let's do actually doesn't matter which one is which, but let's say body and types. We'll do it on the right hand side. So this is just an example of what we want to do, and let's turn this into fold, and our initial value is going to be our two dictionaries, empty dictionaries, and then this is going to take, so the type of this dictionary. Hi Chris, welcome to the stream. Glad you could make it. I'm sorry I missed your 2D visibility ray casting. That looks cool. And I was wondering if you remember this game from the early aughts called Nox. Anyway, it was like revolutionary with that, like the shadows thing at the time. Pretty cool stuff. Okay, so our expected type here, so dict fold goes, okay, so the accumulator comes first and the key and the value. Okay, so what we're going to need to do is, here's our accumulator, and this is going to be the block name. And then, so what we want to do here is we want to get, we want to extract the types, right? So select tail is going to have to return the types for the variables, which means we're going to have to change how that works, which is fine. But now we can say that this is the body, and so let me inline that. Okay, and then we'll say that's the block. And then what we want to do is, so if the set of blocks is here, what we want to do is dictionary, let's say blocks types. Here, why don't we just call that types, and this can be new types. And let's have that be the accumulator. Okay, and then finally, since we're folding, we need to return the accumulator. So our block needs to be inserted. So we're going to insert into blocks our block name and the new block. And then we're going to merge types with new types. Okay, so now we need to fix select tail. And what is going on up here? Oh, right. So this is just body and types. And now it's just complaining about the return value there. So let's go to that definition. And why are we not highlighting here? What's going on? We have a syntax error somewhere. I think it's just complaining that this doesn't return the right type. So this is going to return from a string to an L.type. Okay, now it's just like, hey, your types are wrong. And I'm like, yeah, I know. And this one as well is going to return a string to L.type. Okay. Okay, so what we can do here to simplify some things is just make an empty one, and then the only place that we have to deal with new types being introduced in here is this sequence one, because the rest of them don't introduce new variables, right? So what we can do here is go, we'll say S instructions, S types is that, and then we'll do T instructions, T types, because there may be ones in the tail. And then here we'll do the instructions are append the S instructions to the T instructions. And then the types are just merge of S types with T types. And those should be unique. We're not concerned about that at this point. But what this will do is it'll make it easier for us in all these other cases to just return the empty one. And I feel like in some ways this should be done at a different phase, but it's okay. This is the part where we erase that type information. So we should, since we need it in the interference, the build interference phase, we need to make sure that we are we're passing it along. Okay. So that one's up to date, and now let's go up in here and we can. The thing is, we really only need the types of the vectors, right? It might be nice to have the types of the variables that are getting atomics. That feels like an additional enhancement, though. Okay. So those are the instructions, and we're returning the empty set of types. Obviously here we know this has to be an integer, but we are not going to care. That's an interesting optimization there, but okay. I'd forgotten we've written that. All right, so for assign, yeah, these are all atomics, so no new types introduced. And I'm just making sure that we wrap all this stuff so that we are always returning an empty dictionary of types when we have something that the type information is not relevant. But when we get down here to the assign with the allocation, we will need to add that. Okay, so here's the one that we care about. So let's put curly braces around that, because ultimately what we're going to do is we're going to return this plus we're going to insert in, actually we can just insert into the empty types, right? We're going to insert the variable name and t, and really that's all there is to it. So maybe I didn't need to add those extra braces there. Just needed to add the tuple. Okay, so what did we do? Real quick to review. So we have this empty dictionary of types that we need to pass up as we are processing these statements. Here we are allocating a vector of size amount that has type t. So here's the type information. So we're going to extract that, and we know that this is going to be assigned to this variable. So this variable has this type. So what we can do is take that type there, which remember the type is used to compute the tag for that vector. So we already had to have the type information here. And now we are going to use it to propagate upward the type of that particular variable. So when it comes down to building the interference graph, we can make sure that if that variable is in the type dictionary, then we know it has to interfere with those callee save registers. Right, all the callee save registers. Okay. Okay, so let's go ahead and finish this refactor. Again, we could put, where we're doing these other assignments, we could put variables types in there, even if they're atomic values. But it is not as relevant as when we're assigning something to from a new allocation. Okay. So now we should check the output of select instructions. And I think I need to go to the test. Okay, and the other thing here is we added a new one. And I'm going to say types. Remember previously we did some like, hey, just check that this looks close enough, and we could fill out the rest of this. But I'm going to throw in here and echo the types. Is that going to work? Well, I guess we'll find out. So let's run Gleam test. Yeah, okay. So you can see here that this alloc2 variable gets type vector t of integer t. Alloc6 gets vector t, and so forth. I wonder if that's not sufficient, though, because if we get variables assigned to, so like we get this alloc2 and this alloc6, and those get the types associated, but if they're assigned to other variables, do those variables get those types? And I think that that's relevant as well. And so we need some way to propagate that potentially. One thing that is more challenging as we go through this book is that previously they spent a whole chapter talking about this topic, and here we're down to like 3 paragraphs. So there's an expectation that you're building upon. Yes, but it's also been like at least a month, if not longer, since we started this chapter, and the last time we touched it was in the previous chapter. And we may not have even touched it in that chapter at all. So I'm going to have to refresh my memory on all this stuff. Okay, so let's look. We're not including that. So let's look at the let's look more at the output of this. Maybe what we could do is take a break and have x86 global be formatted. So let's go ahead and do that. Format program, and this is going to take x86 program. So this is input, and this is going to output a doc. So let's import glam doc. And this is a doc.document. Okay, so here the main things are I don't think we did anything here. Yeah, we didn't do any pretty formatting there. That might be useful though. Let's go ahead and put that in here. So format, and really the only things that we care about here are registers and byte registers, I guess. So we'll say format register, and that's going to be a register, and this should return a document. And then let's do, there was a new code action added in 13. No, not extract function. So we'll just add the missing patterns here. And this will be straightforward. It's from string on all of these. Right, and it's going to be basically that. If you missed my Monday stream, this is what we were doing. Creating pretty printer documents from AST, and we got some pretty fun output as a result. And I should just be copying that, but here, RAX, RBP, RBX, RCX, RDI, RDX, RSI, RSP. The only other thing, this added global, so we probably want to add the RIP register. And then we're going to have to update all the places that that's going to get -6 because we will never be RIP. Oops, typo. Okay. And then finally we'll do RIP because we need to, that global thing is actually a register offset. So RIP being the instruction pointer, right? That's this construct here. But when we go to format this argument, what we want it to be is, you know, print out this register. So format the register and then offset it. I suppose we could do that manually. There may be future uses for that register. Okay, so we have the format for assembly is going to be a label for the block. And we kind of did this in our C-like language. So let's look there. Right, so a block would be, you know, have this label with a colon, and then a line break. And then all of the contents need to be joined with lines, right? And then we'll nest them by 2. And we'll put, you know, line breaks at the end. So it's gonna look pretty similar. Okay, so what we can do is we can say input dot body, and we can map. Actually, do just to list, and we'll list map. And we'll say format body, so, or format block, right? And then we'll do doc.concat join, and we'll say put 2 new lines in between those. Okay, so now we need to do format block. And this is going to be a string to an x86 block. Oh no, it's just block here. We're in the same file. Okay, and this needs to return a document as well. So here's where we're going to do that thing like we did here. So I'm going to make a label. But first we're going to say block name, block body is block. Destructure that. So the label is going to be block name. Okay, and then we're going to do something like this. So we're going to take, it's not going to be format tail, but what we can do is we can say block dot body, and we can say this is format instruction, and concat those. We'll concat join with a single new line, and then we'll nest by 2, and we'll group them. And is that how we did the other one? Oh no, we need to prepend the label. This probably needs to be named better because this block is more than just the body, but that'll be okay for now. This is another reason why I like functional languages a lot, is that you can decompose the problem. This is an instruction, and this needs to return a document. And this one is going to be the more interesting one. So we're going to have to add all of the different things here. But it's going to be fairly straightforward. Here we can say doc concat, and we can say this is from string add q. We're going to make a I think we'll put spaces in here because we want to make sure these do not break. Yeah. And then we need to do, this is format atomic, because I think that this is an atomic type, or it's arg. We'll call it format arg. A, comma space, format arg, except that needs to be a document. And what we'll do is I'll throw this up here at the top. We'll say let comma. Format argb. And then let's use the code server here and just generate a function, and it'll have a to do in it, but the correct types. Okay, so then we just have to do the rest of this stuff, which shouldn't be too bad. And this is almost exactly the same. So let's copy pasta. Oops. Why am I doing this? I am doing this so that we can look at the output of select instructions and make sense of it without all of the data structures, right? We're just gonna make it look yeah, this is actually just this label. We want to make it look good so that we can see, does that actually make sense to us? And we don't care about the arity here. The arity is only for knowing how many registers to push. Okay. So okay, this one jump is going to be pretty easy. It is also going to be jump to the label. Jump if is going to be, we need a branch on the patterns. And that's really just what to do. That's really just changing the label. And actually we can say doc from string rather than concat, because we don't need those separate things. We're just gonna, this needs to return a string, and then we'll join it with a space and the label, right? So this can be JE, this is JG, JGE, I believe, JL, JLE. Okay, this is just from string retq. It looks like okay. I kind of want to get some of these ones that have operands up close to one another. So let's see if we can move that up without breaking anything. Okay. Yeah. Because these jump ones are a lot simpler. And honestly, let's push the call queue. You know, this comes when you do that code generation of fill this, it's just gonna spill out all the variants in alphabetical order. So I don't really have, like, it doesn't even look at what's the order up here. Like, it doesn't care about that. It's just like, hey, I'll throw them in there in alphabetical order for you. You're welcome. So we need to deal with that. Okay, comp Q is going to be similar to these things. So let's do that. And this is going to be comp Q. Again, move Q is going to be basically the same. I wonder if we could combine all of these. We can't, because we would need to split it out. That's okay. Okay, this one is going to be move ZBQ. This is going to be neg Q of A, no commas. That's easy. This is going to be similar to that one. Pop Q. Push Q. And when we have this, we can add that to our UI and just like play with some stuff and see what happens. Okay, so this one is more like these. This is shift right. Shift argument right. Okay, set is more like the jumps, if I recall correctly. So let's move sub up. It's more like these. Sub Q. And again, this is XOR Q is more like these. So here, we'll put it into U for now. XOR Q. Okay, so this is going to be okay. And I'm sorry, we need to join this with a space. So if we fill this out, I think it's well, this is all set plus whatever the thing is. So E, G, GE, L, LE. What's going on there? Okay, so this needs to be base format byte reg, because that is always a byte register. So we need to go back over here and go, add similar to this. Okay, so this one is really straightforward, just like the one from above. And actually, let's just go ahead and do this with column editing. Except I need to first of all, we need to fix all of that. Okay, and then we can just fill in the rest. I'm pretty certain that our code will never generate anything but AL, but you never know. Okay, those are the byte registers. This is what you get when you you're working toward an architecture that is basically, I guess, something like 50 years old, and the ISA has not. They haven't changed that much. They just added things on top, and that's how you get, these byte registers. And the reason why they're AH and AL is because the original ones are AX, BX, CX, DX. Those are all 16-bit registers. These are the 8-bit sub equivalents of those registers. So, okay. And then we just need to deal with this. So case A. So if we have deref of a register, so this is going to look like, we're going to concat so the offset is, this is the most complicated one. This one I'm going to cheat. No, I guess not. Let's leave to do. Okay, so for a register deref, it's going to look like offset register, like that. So we need to from string of the offset, and then we have the open paren, and then we have format register of the register, and then we have doc from string close paren. Okay. This one is going to be really just, we'll do it the principled way, since I went ahead and made RIP a register. We'll do it like this, except reg is going to be x86 base R11 or RIP. Okay, immediate value is always an integer, so that's just going to be has this the dollar prefix on it, and then we have int string. Okay, and reg is just format register, and var is just doc from string var name. Okay, so because we still have variables at this phase, we haven't lowered it into a pass where there's no variables. And actually, I don't think that we will ever produce anything but this language. We don't lower it to one without variables. It's just that, well, I guess this, the allocate registers, they're saying patch instructions produces this, and I think it's just will not have any variables left in it. But patch instructions, actually, I think this diagram wrong. Allocate registers should eliminate all the variables, right? It should just be registers and stack locations, which is what we're trying to get to. So we actually need to back up, and we'll need to look at uncover live before we look at build interference and make sure that there's nothing we need to do there. Okay, so all of this to say, let's look at the output of select instructions. let's do format program. Program. So we need to import Glam doc up here at the top. Because this is outputting a string. All right, let's see how we did. Okay, we have a problem here on line 131. We did something wrong. Oh, right. So this is actually A has to be byte reg. It's not an arg. So this is format byte reg of A. Okay. So, yep. Let's back that out. I'm gonna get rid of this. It's not actually that useful. And then over here, where do we put it? We can just say that this is %RIP, and then it's, and then we can simplify this pretty substantially by doing this. We can get rid of the concat. Which, you know, this is exactly what it is. So I don't, you know, the instruction pointer is not something that you usually do. All right, so actually we need to make sure that that echo is sort of like an inspect. So let's do print line instead. And then this is our program. So here's that. You know, that global addressing. But I think that we have a bug there, and I probably have comp q where it should not be. Yeah, I have comp q twice. This is move q. I was like, why are we comparing that? Let's make sure that this is correct real quick. So add q, and q, comp q, move zbq, neg q, pop q, push q, sar q, sub q, zor q, and then set call q, jump, yep. I think we had something in here that would be like, yeah, so we already did a bunch of this, but we did it badly. And it's probably because we were doing string trees and like doing manual indenting, and so I just want to make sure that we like, yeah, see, we're doing some of the same stuff in here. Yeah, want to make sure those instructions are correct. Okay, so when we get there, we can just eliminate all of this code because we have the document formatting. That'll be fun. Okay. Let's go back now. So since we have this formatting, we can add that to our UI. like we were doing on Monday. And then I do want to get to the uncover live, build interference and so forth, because I think that we need to understand. We need to understand that. So we can add our passes here. Select instructions. Let's add that. Sorry, I'm putting those up there. We're doing it in order. Select instructions. Now we didn't do a bunch of the intermediate forms, so we can't do that. And we need to do the inverse now. And the default last pass we can say is select instructions now. And then down here, we will basically do this. And we'll make a clause for, oops. If I can select the right thing. Select instructions. Okay, and then we will do select instructions, and we'll do x86 format program. So we need to import UC langs x86 global as x86. And then we've got another pass. It's that simple to add a new pass to our UI. So let's is it this? Build. Okay. And then we'll start a dev server. And it's building that again. Okay, so we have localhost 1234. Okay, so now we should be able to do select instructions. But let's use our example that we've been playing with in the tests, which is this. So if we compile that, there's our select instructions. I think we might still have a bug in there. Let's have a look. So this is our start. We don't have the prelude or conclusion yet, right? It's just weird that we have this unnecessary move here. That'll get eliminated in the patch instructions pass, but I think it was a probably sequencing of operations thing. So, okay, so we are, yeah. Right, so block 5 is going to be, do nothing. This is move void into _4. Block 6 is calling collect. So this is try to collect 16 bytes, and our root stack pointer is R15. Okay, and then it jumps to block 4. So then it's saying now we have, right, so we're incrementing the free pointer by 16 bytes to allocate our vector. And then it's going to move, this is the tag. The tag is 2. That doesn't seem right. Looks like we have some unnecessary moves there as well. And then no, that's right. It's the size of the vector is 1, and so the second bit is set. But there's no pointers in it because this first one, we have to construct the first one, and then we put that into the outer one, right? So alloc2 is the inner vector because this is a vector of a vector. Okay, so then it's this vec_init1 that we, put here. It has to go into the vector in block 4. Okay, so this is the aspect of the vector set instruction that it compiles out to. This vector constructor is actually allocate and then set each of the individual fields. So this is, hey, your vector set return, move 0 into here. There's a bit here where I feel like the code, the way that was constructed is not helpful because we're going to have to do analysis on this _3, and it's actually just dead. It's never used, but we're going to have to allocate something to it, which is really, really weird to me. So, yeah. Anyway, so this is, increment 8 past the end of R11 and move that initial value into there. And then we, copy the pointer for alloc2 into vec_init5. Which gets used later, and then we're going through this garbage collection dance again. So capture the free pointer, add 16 to it. If we have enough space, and again, here's that unnecessary move. But if we have enough space, then go to block 2, which is up here, and that's just jump to block 1. That's do void, do nothing. And then for if we have to call the garbage collector, we call it if we need 16 bytes. So yeah. So we've got, so finally we jump to block 1, which is I wish it wouldn't fully scroll. Wish it only scroll that side. Let's see if no, that's all right. I don't have this set up correctly. This is a text area, and it should be something else. It should just be like a pre-code with overflow scrolling. Okay, so move free pointer into R11, increment it by 16 bytes, right? So we're moving it, and then this is the tag 130. So length of 1. So we have the, so that would be 128 plus 2, right? So 128 is that first one is a pointer. So we have 6 bytes. Sorry, we have one bit, which is a garbage collector flag. Have I moved this already? There's 6 bits for the length of the vector. This is only 1, so we have 2. So that's where we get the 2 plus 128. And then, so there's 7 bits. So in the 8th bit, right, that would be 127 or 128 would be that 8th bit. That thing in the first element of the vector is 128. So our tag is coming out correct there. Anyway, all right. So then it's so we've got we have the tag set, and now it's moving R11 into Alex6. That feels like it's out of order. Oh no, and it's just moving it back into R11, and then it's setting. It's initializing that field. Okay, yeah, there's a little bit of garbage there. Okay, and then we move Alex6 into temp7, temp7 back into R11. This is the deref, so we're getting the field out of R11, which is this vector we just constructed. We're getting the first field out of it and moving that into temp8. And then we're saying, hey, this is a vector, so move temp8 into R11, and then deref the that field into REX, which is the return value. You can jump to conclusion. Okay, so we kind of walked through this. It makes sense in terms of what we're generating. I don't really feel a need to go into too much more detail there. We did see some things that are kind of weird, like moving out of a register into a variable, moving from that variable back into that same register. So I don't know that we need to add anything there, but yeah. So like this is the fruits of our efforts from Monday. And let me go down here into the UI and say. Oh, right. So this needs to be compile.default last pass. We're gonna, yeah. Let's refresh. Okay, so refresh, and I get the default last pass. That was the bug I needed to fix. This unwrap both has been deprecated, I guess, in use a case expression instead of this function. Well, that's no fun. The whole point of using that is you always had a string. And that only works when both your error types are, and your OK type are the same. That's all right. We'll fix that later. It's just a deprecation. Okay. So what I would like to do now is let's go to Uncover Live, because that's our next thing. But first, let's make a quick commit because we added a lot here. We'll start with what's in the. Oh yeah. Okay. So. So we're gonna update our deps dependencies. Update Gleam and dependencies. That was our what we did with those. So now let's look at the select instructions test. I think I left that in there, the print. I do want to at some point fill out the rest of this test, but I'm not going to do it on stream. I don't think that's useful. This is going to. Oh, I need to add test. Okay, we'll throw that up to GitHub. I needed to make sure that we got the types back so that the next phase could look at the types and it could look at the types and then use them to make sure that they right, this is the graph algorithm, right? And we have the control flow graph. We would need to insert, so for every type, we're going to have to insert conflicts between the variables that are in in that type map that have vectors as their types, and the callee saved registers. So interestingly, I think for Uncover Live, we don't have to change anything. We just have to update this. I guess we'll find out. Because this is just doing... And this will be good to turn it into aliases instead of using the fully qualified module name. Again, making it easier to update next time we come through here. So let's change all the x86 var ifs, except, yeah, let's change all of them because we've already changed the alias to x86, especially dot, yeah. Okay, so now we're gonna have to deal with some things, right? As I expected. Here, hide the shell. Okay, so if we have an arg, so this is going to be that register, right? If we have a deref, and we'll ignore the offset. The global, again, I'm not sure whether we need a register here. We can't allocate RIP, so let's just say it's an empty set. Okay, so now we've got some new instructions as well, so let's add those missing patterns. This is fairly straightforward. And it'll be the same for this. Okay, and then what else? Okay, so write location and instruction. Let's fill that out. So and Q is going to be, you know, always on the right hand side here. Locations in arg B. And we'll ignore A. Why is that the case? Because x86 instructions always mutate their right argument if it's a something arithmetic or a move, like you're only writing to B on move. If it's a single item, then it'll just be that thing, with the exception of pop Q will pop the top of the stack into A. But it also writes to RSP, and push Q writes to RSP as well. So comp Q writes to special register, so that doesn't have any. Okay. All right, so I think uncover live is updated. Let's look at the test. Yeah, we're gonna get, build interference is gonna be broken now. And let's see here. So this is all just complaining about not having anything. And we're just gonna uncomment all of that. I don't know what's reasonable to add for a test here right now. We could take our program and knowing, it's deterministic, right? What it's going to output, because it's going to have the same traversal of the input in each phase. So we could treat that as stable and extract particular blocks and look at their live after sets, because that's really what we care about. But let's go forth. At least there are no compilations errors in there. Update uncover live for x86 global language. Okay. We need to do so. Yeah. Okay. We have uncover live comes after select instructions. Now build interference is the one we actually need to make some modifications in. So let's go there. So let's look at build interference. Now this is going to be x86 global. What we're trying to do here is get the interference graph. So I think that let's see what they say in the text up here, right? So when we construct the interference graph, by adding interference edges between the call live tuple variables and the callee save registers. There's a problem here, I think, that if we just look at our example program that we've been using in our tests, this thing, right? If we just look at this, we know that, for instance, we're jumping to block 5 and block 6, which eventually go to block 4. So our first vector allocation is here in block 4. We're bumping the free pointer, we're adding the tag to it, and so forth. If we've done the data flow analysis down here, we should see that vec_init5 is live, but we don't have any type information about vec_init5, right? We have it about alloc2 because that's where we supposedly moved the allocated vector into, right? So there's some overlapping lifetimes here that kind of bug me with this R11 and the alloc2. So look at that. Like it's like, hey, you moved R11 and alloc2. Of course, you moved it back into R11 for the set. But here we moved it into this other variable. And the type is only known here. The other thing that we could do, and I hesitate to go back and do this, but we did that in select instructions. But in the places where we generated the allocation code, so like we turned the vector, would that be an explicate control? I'm sorry, I'm looking at the tests. Oh, okay. So was it here? Yeah, so we did this here. We took this has type, initializing a vector. And we generated variables for it. This is all the stuff that is generating that GC stuff. But thislalloc language, it has the has type. So I wonder if what we should do so when we go from we're only keeping the type on allocate, but I wonder if we should be have the has type propagated through, because we drop it at this phase, right? We erased it here, with the exception of when we're first allocating it. But if there are cases where, like here, vector set, and vector ref, maybe those should have the has type around them if we can. Of course, technically, that would have to happen up here. So if we go to ltup and its type checker, where's the has type? Okay, so that's just checking the type. But where else are we referring to that? Oh, format. Okay, so it's part of the expression, but we should be, so interpret, that's fine. Right, so if we're constructing a vector, we wrap that with this has type and return the, so this is like mutating the AST, not mutating it, replacing this subtree to say that this thing has this type, and then we put the primitive operator in there. So wherever we're constructing vectors, we wrap the type around. And I think what I would love to do is that's interpret. I feel like number one, the vector sets and the vector refs and the vector length at this level we should wrap those with a has type. I'm concerned it's going to break things because we haven't done that before. But that would propagate into more places the type information. It's going to make the intermediate forms a lot more verbose, for sure. But here it's like we're looking up whatever argument this is, and you know, getting the type of that. So this could be wrapped here. So we could say has type, right, of E and T. And we could do the same here. And we could also do the same here, because we have checked that that vector is has that type. That's going to blow some things up for sure. Because we're probably not going to have handled that in our other passes. So okay, so let's see if we change that. Okay, so parse is fine. Type check. Now we're getting so we have the has type. But we also have right, that's actually fine. Well, it still works. So what we can probably do then is So there's a problem here in that I don't know that this is absolutely necessary, and it may not have even changed anything. But when we get to, because it's possible that this in other phases, remember we're going through this diagram down here, like expose allocation probably throws that away, right? It should actually be here, right? We should have unexpected type wrapper. It should panic. But maybe I didn't do it in the right places. It's also possible that it doesn't panic because we're immediately using that. So like if we change this program to let A is a vector 42, and then in there we do let B is a vector of A, and then we say we do, so we factor that out. We vector ref of B 0. We do vector ref of that of 0. Let's start with parse and make sure that I didn't mess that up. Yeah, okay. So we've kind of broken this direct construction out into let bindings. We type check that. So now we're getting these has types in additional places. No, we're not. Oh, yeah, we are right there. We're not getting it right there. That's interesting. But shrink should do nothing. Uniquify should just rename things. Explicate control should panic. And it doesn't panic. Interesting. Okay. So, because I would expect that our vector ref here, because we did 2 of them, I would expect this one to at least have a has type in it. This B here. Because it's going to look this up in the environment, because this V is a variable, so type checking this expression against the environment, we should get, like, let me put the index here. Actually, let's just do echo vector ref, not dollar, the index, right? So if I do that, yeah, it's fine. And I look at the console. It's not echoing anything. Interestingly, the let binding here. No, but that's the constructor of the vector, right? The vector ref is not getting it. Okay. I wonder if I just need to restart. Wait, let's see what the error is. Let's complain about some tests. Okay, so now it's like, yeah, it can't even compile. So it's not capturing our... It has to do with the tests. I can't compile the tests right now. So maybe we can just comment out that entire test. And we'll go up here and comment this out completely. Uncover live test. Oh, this is L-tup. Okay, what's going on here? Let's go to 191. That is one thing that I sometimes find annoying. I guess it makes sense. But if your tests don't compile, your whole program doesn't compile. Okay, so here it's actually an issue of we need to call expose allocation to get it the correct type. Again, we need to be using aliases here to simplify this change. Okay. Now can we build and run? Okay, so I'm thinking that what will happen is here, rerun, and we lost our program. So let's go back to parse first of all, and let's rewrite our program real quick. Let A is a vector containing 42. And we'll say let B is a vector containing A. And then we have vector ref of B0. And we will do a vector ref of that of 0. And then we have two parens. So that should parse. It parses just fine. Type check. Now we have the additional vector refs. Okay, so the problem was it just wasn't compiling. And now if I go to shrink, it's unchanged. Uniqueify is just renamed the variables. Explicate control, it should panic, right? So we get this unexpected type wrapper here. That I figured we would run into. And that's at expose expression. So that's expose allocation. I feel like we have this in Alloc. So I actually feel like I should just pass it along. And we should not panic here. So I think that what we're going to do here is we're going to say this is we're going to go down into these and we're going to do the wrap. And we'll return la.hasType. And then, right? So then it's not, the other thing here is, we need to like in these spots, right? So the allocate is fine. That gets the type T. Here we need to put the has type on this vector set, right? That way and I think that we need it here too. What does this fold do? This accumulator. All right, so this is starting from the variable because that's ultimately what you wanted to return from the expression. And this is doing the vector sets. This feels a bit messy. The other thing that we could potentially do at this phase is, well, no. I was about to say what we could do is build up that type dictionary. But I think the problem here is that, you know, we get the type on we only get it at the allocation instruction, right? And what I want is it around any place where we reference anything that can contain a vector. And we know that here what we're doing is we are generating the code that lets you allocate the vector. So there are more things that we can tag here with the type. And actually there's this bit here that I think we can extract and say let alloc var is this, and then we can say that we have alloc var here, and this is alloc var. I don't think there's any other places that we need to deal with that. Okay, so we lost our program there. It's fine. Let's go ahead and do that one again. Let's start with the basic one. And let's make sure that we can parse. Okay. Type check throws in all the has types. Lots of has types. So we have some unnecessary ones for sure. I think that maybe what we should do here, so that's at the type check. So let's look at there. I want to like do a maybe wrap. Maybe we'll just make that a function. So let's say we'll call maybe wrap with type, and that's v1 t1. And then let's get rid of that, and we'll make a function down here. Okay, so this is just like we don't need to wrap it multiple times, and I think that yeah, let's do maybe wrap with type here. T right? And then we can do that here. So that if that inner expression returns a has type, we don't wrap it multiple times. And then I think, yeah. You know, all of this is to just okay, maybe that doesn't reduce. No, it did, because we had has type in some places, and here it's like we only need it once. Because it's just a tag on that node. Okay, I need to find where that echo was in this file. Echo. Okay, so we can get rid of that now. And now, okay, so vector ref, vector 42. Here, actually, we can just paste it. Okay, so if we go to parse, fine, nothing new, type check. Okay, so now we have the has types around both the constructions and the references. So you can see that this construction has type vector integer. This construction has type vector of integer. Let's see, the nesting here is kind of throwing me. Okay, so this vector ref 0 has type vector integer, and then this, you know, this vector ref is just integer, so it's not going to have a wrapper on it. So we need to possibly make sure that all of this stuff is propagated down. 340. Okay. I need to figure out how to wrap up. So expose allocation, uncover get. Let's make sure it doesn't erase anything. I don't think it does. I think it just... Where's the has type? Because that's an expression. Yeah, it just recurses into it. That's fine. Okay. And then remove complex operands. So this means that the Elmon alloc needs to have the has type in here as well. And we don't. So I need to make sure that that gets propagated further. The thing is, at this point, I think because these are atomic, we can put the has type here and make ATM a self-recursive. So we'll need to look at remove complex operands and make sure that when it encounters a has type, that it rewraps it. Okay, so we're going to run into a bunch of problems there, but remove complex operands. Okay, so what we do here, the thing is if this is at expression level, it's fine to throw it away. If it needs to be atomic, right? So here we call RCO atom. And then so we're going to do this. And then I'm going to say, I honestly, I don't know if this is going to work, but I'm going to say, that will propagate it in. Oh, wait. There's no has type in there. It's here. What's going on? Right, okay, so there's something else going on that's making the language server not figure this out. Okay, so this is an expression. So RCO atom returns an atomic, right, and a list of bindings and a new counter. So in this case, if we have the has type expression here in a place that needs to be atomic, I want to retain the type to propagate down to later passes, but this return here is going to be like a potentially fresh variable. And probably based on some other things, it will be like var, right? So we have some issues with missing patterns. Yeah, so explicate control. So it's trying to turn it into Alman alloc. We need, or no, it has Alman alloc. We just need to make sure that it has all of the wait, I'm going to expose allocation. I need explicate control. Okay, so I want to panic here. Typed expression panic as. Okay, and then the other thing is here. Honestly, I think this is the thing is we're going to lose that type right there in explicate control. And where do we need it? The phases after explicate control. So and what were we doing? We were throwing it in select instructions. That's where we were grabbing the type. So I think that let's look at the C atomic. I mean, maybe we just throw in here the maybe we put C has type. This feels bad. It feels so bad. But let's do it. And then over here we can say it's has type and just propagate it. Oops, line 438. We need to make sure that we extract that variable. Okay, so then in here in the pretty printing, let's just add the missing pattern, and then we'll say format ATM because we don't actually need the type when we're pretty printing it. It is nice to pass that down, and I feel like I've gotten way out over my skis here for sure. In select instructions, we're going to need to find all these places and yeah, remember how earlier we just made this empty dictionary? and returned the types of the known variables. In all these assignments, we didn't add any types except for this allocate thing. Now we're going to have potentially type wrappers. And honestly, for these inner ones, we should return the type here. If we have it. It's like a variable we don't know. All right, let's go ahead and add the missing patterns. And here we're just going to go on the inner one for now. And we'll ignore that. But what I want to do is down below where we're saying select, where we're calling select atom, that this will return the type, or optionally return the type. Let's go ahead and do that, and then we'll fix it. So it's l.type, or we'll just say it's just type, I think. No. Okay, so this one is going to be integer t, right? And actually this is going to be option of type. So this will be some, yeah, it's not in the thing by default. So we need to do Gleam option type option some none. Okay, so here we'll do none because we don't know what it is. For here we know it's some Boolean t, right? Void, here we know it's some void t. And here, what we'll do is, it's like if we don't know what the inner one is, so we'll say option dot it's option, not unwrap. We want to say option or, yeah, option or sum of t. So, and this is actually, we need a binding there. We'll say let a of inner t. This is inner t, and this is select ATM of value. So this is like if this inner type, if this inner value, which is an atomic, logically speaking, this should not exist, but if we have a wrapper then we're saying it has this type. This inner thing could return a type, but it's probably a variable. We have to return none there because we don't know what it is. But here, if we have a wrapper around it, we can say that, yeah, either you have something inside here, or we're going to return this type. So now, what we can do, we'll have to redo all of this. And honestly, I'm kind of running out of steam. I'd like to take a bio break, but maybe we'll resume this next time, because I think that we've solved an important, or we started to solve an important problem here. We erased our types too early. We didn't like generate a dictionary of the types for all the variables we were generating. And that's way more complicated than just throwing it in the AST with these little wrappers. So I think that there will be fruit born from that as we go forward, and I'd like to get to the point where we can take advantage of that and then go into built-in interference with these are all the variables that we know about and all their types. And if they exist in there, honestly, no. If they have a type at all, we know what they are, and then the build interference can go, is this a vector type, and I can go ahead and create edges between the interference edges between the things that are vector types and the particular registers they should never be assigned to. So that's where we should go, and we'll pick that up next time. Thank you for bearing with me, and see you next week.